All right, we want to be able to graph any type of function and be able to say any asymptotes, intercepts, and the domain and the range. This first function is an absolute value function. You should know that the absolute value parent function has a vertex at 0, 0. This is y equals absolute value of x. And has a slope of 1 and a slope of negative 1 on the two parts. So the transformations we should notice is that this gets shifted 1 to the right and 4 units down. That's what these two transformations do. And then this, because there's a negative that's multiplying times the absolute value parent function, it reflects across the x-axis and vertically stretches it by a factor of 2. So I like to take this vertex and shift it, instead of being at 0, 0, it gets shifted to the right by 1 and down by 4. So it'll be right here. And then the instead of going up, it'll open down, and the slope will be 2 instead of 1. So it makes this V shape like this. Okay. So let's state the intercepts. Well, there aren't going to be any x-intercepts because it's facing down, but there is a y-intercept right here at 0, negative 6. That's the y-intercept. There is no asymptote here. The domain, it keeps going to the left forever, keeps going to the right forever. The domain is all real numbers. The range of this, well, it's all the y values that are less than or equal to 4. So we could say y is less than or equal to 4. Or, more commonly, we're going to want to use interval notation where we go from bottom to top. And in interval notation, this would be all the y values from negative infinity to 4, including 4, not including negative infinity. We never actually get there. Okay? So all the y values are between negative infinity and 4. That's how we read that. All right, let's look at this next one. This is an exponential. And you should know that the exponential parent function makes a shape like this and has a point at 0, 1, because anything to the 0th power is 1. This got shifted 2 to the right. So since this got shifted 2 to the right, I'm going to take the point at 0, 1 and move it over to here. This is an exponential with a constant multiplier of 2. So it's 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16. We know that exponentials have a constant multiplier. They grow very, very quickly, very fast. And then going to the left, it gets divided by 2, divided by 2, divided by 2, which is what forms this asymptote to the left. So the intercepts are, there's a y-intercept at 0, comma. In case we don't know exactly what this is, we can always just plug in 0. When x is 0, 2 to the negative 2 power is, well, we know about exponents. This tells us to divide. This is 1/4. 1 divided by 2 times 2. There is no x-intercept because there's an asymptote here. The asymptote is at y equals 0. We can use limits to write this. This is going to be really important in calculus. The limit as x goes to negative infinity of f of x is equal to, this says that as x goes more and more towards negative infinity, the y values will equal 0. The y value gets closer and closer to 0 as x goes to negative infinity. Notice that as x goes to infinity, as x goes to the right, the y values get bigger and bigger, and that limit goes to infinity. The domain is all real numbers, or we could say from negative infinity to infinity. The range is all the y values that are bigger than 0. I'm just going to do everything in interval notation from now. So it's all the numbers between 0 and infinity, not including 0. All right. Here is a log function. You should know that the log parent function is the inverse of exponential. They look like this. You should know a log function looks like this. They grow very slowly, and they have an important point at 1, 0. So this log function got shifted 3 to the left. Remember, it's backwards from what you would think, and 5 up. So I'm going to take that important point at 1, 0 and shift it 3 to the left and 5 up. Notice that there's no point at 0, 0, so I'm not shifting a point from here 3 to the left, 5. There's no point. There's no point at negative 3, 5. That's not a point. But there is this point that got shifted. I'm also going to shift the asymptote. The asymptote was at x equals 0, but that gets shifted 3 to the right as well. So instead of being at x equals 0, it'll be at x equals negative 3. And from here, I feel comfortable just following the asymptote and having it grow. Something like that. I don't need it to be perfect there. All right. The intercepts. When x is 0, this is the y-intercept. When x is 0, y will be the natural log of 3 plus 5. And that can't be simplified, so we just leave it like that. There's also a x-intercept. And for this one, we need to set the y equal to 0 and solve an equation. 0 equals natural log of x plus 3 plus 5. Subtract 5 on both sides. And hopefully you know how to solve all types of equations already. To undo a natural log, we do e to the power of both sides. E to the negative fifth is 1 over e to the fifth, and that can't be simplified anymore. And so x equals negative 3 plus 1 over e to the fifth. And that should make sense. It's just a little bit to the right of negative 3. So the other one is negative 3 plus 1 over e to the fifth, comma 0. That's the x-intercept. There's an asymptote at x equals 3, and the domain is from negative 3 to infinity, but there is no value at negative 3. And the range is all real numbers. This quadratic has normally we know this quadratics have a vertex at 0, 0. This quadratic got shifted to the right by 5 and down by 6, and so that's where its vertex is going to be. So here's its vertex. This vertically stretches it by a factor of 3. So normally from the vertex, 1 squared is 1. So normally there would be a point here and here, but 1 squared is 1 times 3. Those get multiplied by 3, so it'll be up by 3 from the vertex. So it'll be right here. The next point would normally be 2 away from the vertex. We would have 2 squared. 2 times 2 is 4. That would be right here. But those get multiplied by 3 as well, vertically stretched by a factor of 3. And so 3 times 4 is 12. So it's 12 up from the vertex. It'll be all the way up to, let's see, 10, 12. Right here. So here we are. Here is our quadratic. Yuck. It's kind of did I mess? Oh, I messed this point up. That's why it looks weird. I was like, that's an ugly quadratic. Okay, I apologize. All right. So the intercepts. Well, the y-intercept is going to be way up high somewhere. The easiest way to do it is just to plug in 0. So it's going to be 0, comma. When we plug in 0, 0 minus 5 is negative 5. Negative 5 squared is 25. 25 times 3 is 75. 75 minus 6 is 69. The x-intercepts don't look like they're at exact points, but let's go ahead and solve for them. It's when y is 0. So 0 equals 3 times x minus 5 squared minus 6. There's only a single x here, so I'm just going to get the x by itself. So there's no x squared and an x. We can just isolate it. So I'm going to add 6 to both sides, divide by 3, take the square root of both sides to cancel out the squaring. But when we take the square root on both sides of an equation, we need to remember to do plus or minus. And so x equals 5. We're going to add 5 to both sides, plus or minus the square root of 2. And that makes sense, right? Here is... I messed something up. Uh-oh. Well, you're just going to have to pretend that I did this graph right, because I did not. This vertex should have been right here. And the whole thing is shifted over by a little bit from where it should be. I apologize. This point was correct. So it should look like this. Oh man, what a gross graph. I apologize. So this now makes sense because the vertex was at 5, and if you go to the right by the square root of 2 and to the left by the square root of 2, those are the two x-intercepts. So negative 5 plus or minus square root of 2, comma 0. Those are the two x-intercepts. There are no asymptotes here. The domain is all real numbers, and the range is all the y values greater than or equal to negative 6, so from negative 6 to infinity. Okay, let's see, any other important ones? Oh, this cubic. Let's see, this cubic, this is a new one. You may have forgotten how to do this. The easiest thing to do is to factor this and see where the x-intercepts are. So we're going to factor out the negative x squared, that's the common factor. And it'll be times x minus 2. And this is just another way of writing f of x. So to make this equal to 0, x would have to be 0 or 2. And from here, we need to remember how to use our in behavior. Remember, cubics look something like this. Because they're an odd polynomial, they go down to the left and up to the right. And because this factor, this is important, and it's going to come up in calculus a few times, because this factor is squared, there's a multiplicity of 2 there. And so our cubic function would normally look like this, but because there's a negative as a leading coefficient, the in behavior goes up to the left and down to the right. So it ends up looking like this. So it's going up to the left. Because there's a multiplicity of 2 at x equals 0, it bounces off there. It doesn't change signs. And then it does cross through x equals 2, and so we end up with a graph that looks like this. There's an intercept at x equals 0 and x equals 2. There's no asymptotes. The domain and range are both all real numbers. All right, almost done here. This is a square root function. Let me turn on the light. The clouds are coming outside and it's making this hard to see. Maybe that makes it a little bit better. I don't know. This is a square root function, and you should know that square root functions have a vertex at 0, 0, and look like this. This one got shifted to the right by 1 and down by 3. So there's a vertex at 1, negative 3. It's also getting vertically stretched by a factor of 3. So normally we would do square root of 1 is 1, but that gets multiplied by 3. So square root of 1 is 1, times 3 is 3. The next square root we can do is square root of 4. So when we go 4 over from the vertex, square root of 4 is 2, but that gets multiplied by 3, so it'll be 6 up. And the next one would be square root of 9, but that's off of our graph. So we get a graph that looks like this. There is no x-intercept. There's no y-intercept. There's an x-intercept at 2, 0. There are no asymptotes. There is a domain of, the domain is all the numbers between 1 and infinity. The x values go between 1 and infinity. And the y values go between negative 3 and infinity. All right, last type of graph we should know is a rational function. And this is a transformation of the parent function y equals 1 over x. And you should know that the function 1 over x looks like this. It's got 2 asymptotes in it. It has a point at 1, 1, and negative 1, negative 1. And so this got shifted 2 to the right. So the vertical asymptote will be at x equals 2. It got shifted 1 up. So the horizontal asymptote will be at y equals 1. And it got vertically stretched by a factor of 2 because this is the same as 2 times 1 over x. That's 2 over x. So it got vertically stretched by a factor of 2. So instead of being 1 up from here, it's 2 up. And instead of being 1 down from here, it's 2 down. It got vertically stretched. And so we get a graph that looks like this. There is an intercept at 0, 0. That's the only intercept. There are asymptotes at y equals 1 and x equals 2. The domain is, we're going to write this in interval notation. The domain, there are x values from negative infinity until 2, and then again from 2 to infinity. The way we write that is negative infinity to 2, union 2 to infinity. The range is all the y values between negative infinity and 1, and then again from 1 to infinity, but it doesn't include 1. So we write that like this. All right, hopefully that helps you with how to graph everything from Algebra 2.